Okay, so here we go on quiz number 9. So these are all questions from the homework. Test the given claim. Identify the null hypothesis alternative. All right, so here we go. Among 2015 passenger cars in a particular region, 235 had only rear license plates. Among 315 commercial trucks, 46 had only rear license plates. A reasonable hypothesis is that commercial truck owners violate laws requiring front license plates at a higher rate than owners of passenger cars. Use a 0.10 significance level to test that hypothesis. All right, so let's write down the claim. What is the claim? What's being said here? It says a reasonable hypothesis is that commercial truck owners violate the laws at a higher rate. Trucks higher than the cars. That's what they're basically saying. The trucks violate the thing more than the cars. So that's population. Well, which one's the cars and which one's the trucks? Which one came first? I guess the cars came first. That'll be population 1. So we'll just say population 1 is the cars. Population 2 is the trucks. Population 1 was the passenger cars. And then population 2 is the trucks. So population 2 is the trucks is higher than population 1 is what they're saying. Or another way you can put that is population 1 is lower than population 2, right? Same thing. Population 2 is the bigger one, or population 2 is the bigger one, or population 1 is the smaller one. Another way to say the same thing. So that's what's being claimed. So the null hypothesis, of course, is always equals. So P1 equals P2. So the alternative hypothesis, H1, is going to be this. Both these are right. It doesn't really matter which one, but it's just habit. If you notice, they always put P1 first. So it's just the style they're using. There's nothing wrong with the other way. It's just the style they're using. We'll put P1 first. So trucks are higher than cars. In other words, we're saying cars are lower than trucks. Same thing, right? If trucks are higher, then cars are lower. Same thing. All right, that's the claim. That's the claim being made, that the cars are lower, right? Cars are here. Cars are P1. Trucks are P2. The trucks are higher. Cars are lower. That's the claim. So which one of those is the right claim? Looks like A, option A, not the other ones, has the right claim for us. All right, let's keep moving. Identify the test statistics. So we go to our calculator. Okay, we go to our calculator. Let's go look at the exam 4 notes. And so here are the exam 4 notes that I gave you. So we're doing 2 proportions. That's what we're talking about here, right? These are 2 percentages, aren't they? 2 proportions. That's what we're saying. You know, which is a higher percentage? Does a higher percentage of trucks violate the law than cars? It's percentages we're talking about. Proportions, in other words. Okay, so we're going to use the 2 proportion Z test because we're doing a hypothesis test. Let's do it. So we go to our calculator, do the 2 prop Z test on our calculator. Go to stats, test, down to 2 prop Z. All right, it's going to ask us for X1. Now, what's X1? Population 1, remember, population 1 is the cars. Population 1 is the cars. So the cars, when it comes to the cars, 2015 passenger cars, 235 had only rear license plates. They didn't have a front license plate. So that's 235 that violated the law out of N1. The number of cars total in this sample is 2015. So there's for the cars. We made the cars population 1. And then, for population 2 is the trucks. Population 2, 315 commercial trucks, 46. That's the trucks. The trucks violated the front license plate law. So we put that information in, and we're doing a less than test. So we tell our calculator less than. Hit the calculate button, And here's what I'm getting. A test statistic minus 1.49, p-value 0.068. And so we're doing the 0.10 significance level. So that is 6% is less than 10%. So if the p is low, that p is low, that p is lower than the significance level, the null, the HO, must go. P is low, the null must go away. So the null is out. We cross out the null. We accept the alternative hypothesis, the claim that the car number is lower than the truck number, or the truck number is higher than the car number, whichever way you want to say that. Let's go to the next screen where we can get a conclusion on that. So that's going to be conclusion A. We're going to reject the null. There's sufficient evidence to support the claim. The commercial truck owners violate laws higher rate than the cars, right? Right? We crossed out HO. We rejected the null. The null had to go away because the P was low. The percent chance of luck. That's what the P value is. There's only a 6% chance that this data from cars and trucks that we're looking at was just lucky data and the trucks just happened to violate it more. No. This is too many cars and trucks. That's not very likely. There's only a 6% chance of luck. That's less than the significance level 10%. So we believe the data is reliable. And so we believe the claim that trucks are higher than cars or cars are lower than trucks, same thing. So that's A. Now, down below, they want us to do a confidence interval for the appropriate. They want us to do an appropriate confidence interval. Remember how that works? Let's look at the notes. So here we go again. Suitable confidence interval. How do you do it? Well, it depends on H1, doesn't it? Let's go back. What's our H1? There it is. It's a less than. Our H1 is less than. So for less than, so it's this case here, 1 minus 2a. So H1 is less than. So the confidence level is 1 minus 2a. What's the a here? There it is. The a is the significance level, 0.10. So plug in the 0.10. So the C level is 1 minus 2 times 0.10, which is 1 minus 0.20, which is 0.80. So it's an 80% confidence interval. So come down here, going to do an 80% confidence interval. Now, let's go back to the to our notes. So we're doing the 2 proportion. We're going to do the 2 prop Z interval. 2 prop Z interval instead of 2 prop Z test this time. So we'll go there and do that. So 2 prop Z interval on our calculator. Two proportions Z interval. And it'll already have in the same x1, n1, all that. It'll have this information already in there. You just got to put in, let's go ... confidence level 0.80, right? Because we figured out it was going to be an 80% confidence level. Hit the buttons on your calculator. You should get negative 0.0565. And the other one, negative 0.0023. Rounded to 4 decimal places. And so, now what does that mean? Because the confidence interval is, let's do this on a number line. So that confidence interval went from negative 0.0565 to negative 0.0023 with 0 somewhere over here, right? And then positive numbers over there. So those are both negative numbers. We are 80% sure that the true difference for all cars and trucks, the true difference is somewhere, the difference in the proportions, the true difference in the percentages, is somewhere between negative 0.05 and negative 0.0023, which means we're really sure 0's not in there. If 0's not in there, then they're not equal. right? Remember, because this is the difference. We're taking population 1 minus population 2. If that equaled 0, right, what does that mean if you subtract two numbers and it equals 0? Like 7 minus 7. It means they're the same number. The only way you're going to subtract two numbers and get 0 is if they're the same number. So if their difference was 0, they'd be the same. If their difference is not 0, they're not the same. So we are 80% sure that the difference is somewhere is a negative number, not 0. 0's not in there. So we're pretty sure that the difference is not 0. They're not the same. Because the confidence interval limits do not contain 0, there is a significant difference between them, right? They don't contain 0. Their difference can't be 0. Well, at least we're 80% sure. Their difference is, we're more than 80% sure their difference is not 0. There is sufficient evidence to support the claim that they're different, right? There's strong evidence here because we're confident, 80% confident, the difference is negative. It's not 0. So difference is not 0. They have a real difference. All right, number 2. A simple random sample of front seat occupants involved in car crashes is obtained. Among 2931 occupants not wearing seatbelts, 27 were killed. Among 7,772 occupants wearing seatbelts, 20 were killed. Use a 0.05 significance level to test the claim that the seatbelts are effective in reducing fatalities. Okay, so we've got two populations here. So population 1, proportion 1, is we're talking about 2931 not wearing seatbelts. It's the percent, or the proportion. I should just say the proportion. The proportion that died no seatbelt. Proportion P2 is the proportion that died and they were wearing a seatbelt. Okay, so proportion 1 and proportion 2. Let's go to it. What's the claim on this problem? What are they claiming? They claim that seatbelts are effective in reducing fatalities. So in other words, those that wear seatbelts have less. That's what we're saying. Those that wear seatbelts have less fatalities. That's what we're claiming. Because that's what it means, right? For seatbelts to be effective in reducing fatalities, they're making those who wear seatbelts have less fatalities. So we're saying P2 is less. So the claim is P1 is more than P2. The P1's more, right? Those that have no seatbelts have more fatalities. Those that wear the seatbelts have less. That's what's being claimed. All right, let's write our null and our alternative hypothesis. The null is always that they're equal. The alternative is P1 is greater than P2. That's the claim. Okay, we go to our calculator. We do the 2 prop Z test. As you know, exam notes, 2 proportions, 2 prop Z test. Okay. Okay, so X1, first population, those who died, so X1 in 1, or I'm sorry, those who had no seatbelt, so no seat belt, X1 in 1, so 2931 not wearing, that'd be the number not wearing, 27 were killed. And the next 2 into 7772. This is the seatbelt people. Wearing seatbelts, 20 were killed. 20 killed. All right, and we're doing a we're doing a greater than test here. So we choose greater than and hit the calculate button. Oh, I forgot to say this is our options right here. It's F. I kind of wrote over the top of it. This is our option right here, F. So this is no seat belt group. This is the seat belt group. We choose the greater than, hit the calculate button, and here's the numbers I'm getting. 4.63 for the Z value, and I'm getting a 0 for the P value. Now the way I'm seeing that is it actually said on my calculator, it said 1.8141359, but then it had this E minus 6. Remember what that E minus 6 means? We've had that a couple other times. That means you need to take the decimal. This means decimal left 6 places, right? So it's right here, and then I go 1, and then 2, 3, 4, 5, 6. So those all bring in zeros, don't they? Right? Because if you move left 6 places, the first jump goes to the edge of the number. The other 5 jumps bring in zeros. So it's 0.5 zeros and then 1814. So that p-value rounds to be 0. If you round to 3 decimal places like they want me to do, that rounds to 0. That's a p-value of 0. So remember, you watch out. So watch out whenever they have that E at the end. If it's negative, that means go to the left that many places. Left 6 places. So that's effectively that's a 0 for the p-value. Okay, so that's a 0. So what does that mean about our conclusion? Well, let me go to a fresh screen here. Well, wait, I got to finish this one. My p-value is certainly really low. It's 0. So they want me to test at the 0.05 significance. That's certainly less than 0.05. Right? 0 is less than any positive number, so less than 0.05. So the P is low, so the HO, the null, must go away. When the P is low, the evidence is strong, the null goes away. We believe H1, the claim. In fact, there's strong evidence. There's basically a 0% chance of luck. It's so low, it rounds to 0%. P-value is the probability of luck. These results are so strong, such a higher percentage of people not wearing a seatbelt die from a car accident than people that wear seatbelts. The percentage is much lower for those who are wearing seatbelts. That it's beyond reasonable doubt. We just don't. There's a very small chance. Could it be just luck? It was just the ones wearing seatbelts were just lucky accidents that weren't going to get hurt anyway. Yeah, that's possible, but it's very unlikely. It's basically a 0% chance of luck. We don't believe it was luck. We believe the seatbelts are making a difference. That's reasonable. Less than a 0.05 chance. So we believe the claim. We reject the null hypothesis assumption, believe the claim that P1 is greater than P2, meaning the death rates are higher for those not wearing seatbelts. The p-value is less than the significance level. So reject the null hypothesis. There is sufficient evidence to support the claim in this case. Let's go to the fresh screen. Now they want us to find an appropriate confidence interval. How do you find an appropriate confidence interval? Remember, we learned how to do that. Suitable or appropriate confidence interval. Remember how that works? It's all based on H1. H1 in our case is, our H1 is greater than. So H1 greater than or less than, the confidence level is 1 minus 2a. So the confidence level, 1 minus 2a. What's the a? What's the significance level? It is right there. Significance level 0.05, that's our a. Put that in. 1 minus this. 2 times 0.05 is 0.10. 1 minus 0.10 is 0.90. So it's a 90% confidence level. So confidence level 9. So you go on your calculator then. So getting again back to here, 2 proportion. We're going to do 2 proportion z interval now. So we do 2 prop z interval. And when you go to 2 prop z interval, everything will be there already for you as far as the x1, n1, x2, n2. It's already there. It's the same as it was. That's great. Choose your confidence level then to be 0.90, like we talked about, and hit calculate. And what you'll get when you do that, if you round it, 0.004, round to 3 places, 0.004, 0.010, rounded to 3 places. That's what you get. I had 00969, so I rounded to 010, 010. All right, so what is the conclusion based on that information, that confidence interval? What's the conclusion based on the confidence interval? Well, the whole issue is whether 0 is in the interval or not, right? Let's draw the interval. Here's 0. This interval goes from 0.004 to 0.010, so it's right there. We're 90% sure that the real difference between those wearing seatbelts and those not, the percentage that die in a car accident, we're 90% sure the real difference is somewhere between 0.004 and 010. In other words, 0, not likely. We're 90% sure that 0 is not in the interval. So the difference is not likely to be 0. The difference is not likely to be 0. So there really is a difference then, right? Because if the difference is 0, that means there's no difference. But we're saying the difference is not likely 0. We're 90% sure it's not 0. When the difference is 0, that's where they're the same. When two things have a difference of 0, they're the same. So we're 90% sure that the interval's here and their 0's not in there. They're not the same. They're not the same. We're 90%. We're actually more than 90% sure they're not the same, because the confidence interval limits do not include 0. It appears that the two fatality rates are not equal. They're not the same. Because the confidence intervals include only positive values, it appears that the fatality rate is higher for those not wearing seatbelts. And what's the conclusion? C. The results suggest that the use of seatbelts is associated with lower fatality rates than not using seatbelts. The evidence is very strong. Okay, number 3. Large samples of women and men are obtained, and we're measuring their hemoglobin levels. Okay. The measures from women correspond to population 1, men are population 2. We're taking the difference, notice. So this is women minus men. Men is population 2. Women minus men, we're saying the difference somewhere between minus 1.76 and minus 1.62. So the difference between women and men, somewhere in that interval, is what we're saying. Okay, so how's this going to work? What are we trying to do here? Well, if that's the case, what does the confidence interval suggest about equality of the men hemoglobin level and the women? Okay, well, I made a sheet. Here, I'm going to switch over now to this is exam 4 notes. This is the main thing that'll help you get ready for exam 4. It helps with all the homework and the quizzes as well that are here in exam 4, chapters 9, 10, and 11. So what it basically says, if you have a confidence interval, you could just check out what kind of confidence interval you have. What do we have? We have all negative values, don't we? Our confidence interval, if you put 0 right here, ours goes from negative 1.76 to negative 1.62. There's our confidence interval. We are pretty confident that that our true value is right in there. 0 is not included. So if you have this all negative, that's what we have. 0 is not included. It implies that the confidence that the difference is less than 0, meaning that mu1 is less than mu2. Do you see what that's saying? Because these are negative values, women minus men, we're pretty confident that the women minus men difference is negative. It's between negative 1.76 and negative 1.62. We're very confident, 95%. We're 95% sure that the difference is between negative 1.76 and negative 1.62. The difference, that's women minus men. So if you're taking women minus men and you're getting a negative answer, that means the women number must be smaller, like 7 minus 9 is negative 2. The only way to subtract two things and get a negative answer is if the first one is smaller and the second one is bigger, right? The women number must be smaller, the men number must be bigger, because when you subtract them, you're getting negative. We're 95% sure the difference is some negative number. It's not 0. So, because the confidence interval does not include 0, it appears that there is a significant difference between the levels, right? If 0 was in the interval, then their difference could be 0. If two things have a difference of 0, they're not different. They're equal. But 0 is not, right? Remember, 0 is where they're the same. If the difference between two things is 0, they're the same. Well, sameness, 0, same, is not in our interval. So we're 95% sure, because it does not include 0, that there is a significant difference. Write a brief statement. Here's our answer. 95% confidence that the interval between negative 1.76 and negative 1.62 actually contains the value of the difference between the two population means, meaning the true difference between all women and all men. That's always what we're going after in these statistics problems. We take a sample of a few men and women or a few whatever, and we're trying to find the truth of all men and women about whatever the difference is in the case you're looking at. In this case, the average hemoglobin level. We're trying to say for all men and women, is there a difference in their hemoglobin level? Well, we did a little study with a few men and women, and our results give us a 95% confidence that the real, true difference is between minus 1.76 and minus 1.262. That actually contains 95% sure that the true difference is somewhere in that zone. Finally, we have Part C. Okay, let's look at that. Here, I'll go to a fresh screen. So, express the confidence interval with measures from min being 1 and choose the correct answer. Oh, so now they want us to turn it around. So, see how they're putting men as population 1 now and women as population 2 now? So, they're just saying switch it around. Before, it was women were population 1 and men were population 2. So what happened? So we had the interval from up here. It went from negative 1.76 to negative 1.62. If you switch that around, here I'll put it down here, 1.76 to 1.62. Here's 0. If you switch it around, those both become positive. This becomes positive 1.62. This becomes positive 1.62. 0.76. So that's if you switch, because before we had women minus men before. Now we're taking men minus women. So we switched it around, so it's just going to change the signs. So the answer on this one is D, positive 1.62 to positive 1.76. Okay, so here in number 4, we're looking at, okay, study was done, proctored and non-proctored tests. So here we have proctored tests and non-proctored tests. Basically, we're testing to see if, when a test is non-proctored, that means nobody's watching them take the test. So they might cheat, is the question. And so we're going to do a study to see if they get like significantly higher scores on the test on average, the group that's non-proctored. Then we might suspect that a few of them are cheating. So here we go. So in the proctored group that had a proctor watching them, 33 took the test, and their average, X bar, their average was 77.81. Standard deviation, that's average distance from the middle, 10.59. So the other group, 30 took the test non-proctored, nobody watching them. 87 was the average. Now that's higher. That is 10 points higher. So we might suspect some kind of cheating. And that was 18 standard deviation. That's typical distance from the middle. That data set's more spread out. All right. So what is the claim on this one? It says the claim somewhere. Oh, there it is. Test the claim that the students taking the non-proctored, the ones that were, nobody watching them, they got a higher mean score. So that's what we're testing. Okay, so the claim, I'm going to write the claim up here. The claim is that the non-proctored got higher. Which one's that? That's the mu2. So we're saying that the mu1 is lower than the mu2. Right, we're saying this one's higher, this one's lower. That's the claim. Because this is the non-proctored. Non-proctored is higher, and the mu1 is lower. The mu1, the proctored, is lower. That's what we're claiming. So let's write our null and alternative hypotheses. The null, is always equal. So the alternative must be mu1 less than mu2. That's the claim being made. You know how the evidence goes. It's always weak evidence. For the null, it's strong evidence. For the alternative hypothesis, if evidence is strong, we believe the alternative hypothesis. Okay, on our calculator. Now we're talking about means now. Let's go to our study notes. Where's our notes for this? There it is. This is 2 independent means. All right, these are just 2 independent groups. The 2 groups are not matched in pairs. No, they're not. They are independent. Use the 2-sample t-test. Here we go. So this just 33 people took it proctored, 30 were not proctored. 2 separate independent groups, not matched up in pairs in any way. So we're going to do the 2-sample t-test on our calculator. So I go to 2-sample t, and then it'll ask you, where's your input come from? Does it come from data or stats, meaning summary? Oops, I wrote states. Summary statistics. Well, ours is coming from summary stats, right? We don't have a list of data. We don't have like all 30 scores for the non-proctored people and all 33 scores for the proctored group. No, we just have the summary of those numbers, right? The average for both and the standard deviation for both. Those are called summary statistics. So we choose stats, and then it asks you for x1, sx1, so x1. That's the, oh, wait a minute, I'm sorry. I'm in the, oh, yes, no, that's correct. X1 is 77.81. SX1 is the 10.59 right here, those 2 numbers. N1's the number in group 1, which is 33. And then it's going to ask me for the same stuff for group 2. It's going to ask me x2, sx2, and n2. So it's 87.61 is the average for group 2, 18.31 the standard deviation for group 2, and the number in group 2, 30. So put all that information in, and then it'll ask you what kind of H1 we have a less than, so it's a less than test, and pooled is always no. And then hit calculate, and the test statistic comes out to be minus 2.58, p-value 0.007 on that, 007. There we go. So now the question is, how does that compare to the significance level? That's certainly less than 0.05, less than the significance level. So if the p is low, it definitely is. The p-value, the percentage chance of luck, is really low. So the p-value is low. The HO, the null, must go away. So bye-bye to the null, because evidence is strong. There's a low chance of luck. Evidence is really strong. We believe the claim mu1 is less than mu2 on this one. So that is D down here. Reject the null. There is sufficient evidence to support the claim. So there we go on that. Let's look at the last part. Okay, so to the last part. Down here in B now. So construct a confidence interval. Suitable. So remember how that works. Let's go back to the notes. It's all about, so for a suitable confidence interval, it's all about your H1. If your H1 is less than, you do 1 minus 2a, right? Remember the notes that I gave you? If I can find it, there it is. Suitable confidence level for H1 greater than or less than, you do 1 minus 2a. So 1 minus 2a, what's the a here? The significance level, 0.05, that's our a. So the C level, the appropriate confidence level, that'll be the same as the hypothesis test. We plug in 1 minus 2a, 1 minus 2 times 0.05, 1 minus 0.10, 0.90. So we need to do down here a 90% confidence interval test. So to do that, we're going to do a 2-sample T interval. So go to 2-sample T interval instead of T test, because we're doing a confidence interval 2-sample, because we have 2 samples. They're going to ask you if your input is from data or stats. It'll automatically be on stats, and it'll already have all of these values in there. So you don't need to do it again. Just go down to the bottom and choose your C level to be 0.90% and tell it to calculate, and you will find that you get the answer negative 16.26 to negative 3.44. So notice that's all negative, right? If you did here, if here was 0, that's negative 16.26 and negative 3.44. We're 90% sure the true difference is in that zone, right, which is the testing. So we're 90% sure that the difference between the people that had a proctor and didn't is somewhere in this negative zone. In other words, 0 is not included. So and remember what 0 means. 0 means that's where they're the same, right? Because if the difference between two things is 0, they're equal. They're the same. So wherever 0 is, that's the mark of sameness. If you subtract two things and you get 0, they're the same. So 0 is not in our interval. So we are 90% confident, more than 90% confident, that 0 is not in our interval, so they are not the same. So does the confidence interval support the hypothesis test? Yes, certainly, because the confidence interval contains only negative values. Therefore, we don't believe they're the same. We reject the null that would say they're the same, like we did in the original hypothesis test. Confidence interval and hypothesis test always telling the same story. Okay, number 5. Listed in the data table are amounts of strontium-90 in a simple random sample of baby teeth from 2 different cities. Okay, let's go see that data. There it is. There's the amounts of strontium-90 from the baby teeth samples in City 1 and City 2. I don't know what strontium-90 is exactly, but we're looking for it in baby teeth. So we're talking about 2 populations. They want me to test, where's the claim? There it is. Test the claim that the mean amount of strontium-90 from City 1 is greater than City 2. So there's the claim. So claim that City 1 is greater than City 2. City 1 greater than City 2. All right, let's write our null hypothesis and our alternative hypothesis. Null is always equal. Mu1 equals mu2. The alternative is the claim, mu1 greater than mu2. That's our claim. You know how evidence goes. It's always weak evidence would make us stick with the null hypothesis, and strong evidence that we would need to go with the alternative hypothesis. Okay, so now this data, now you might, here's a case where you might get confused and think, hey, maybe that data is matched pairs. No, it's not matched pairs. Why? This is just a bunch of people from City 1 and a bunch of people from City 2. This isn't like husband and wife teeth or, couples teeth or, people living in the, there's no matching of any kind. They're just 2 totally independent samples. So, no, it's not matched pairs. These are independent samples. I think it even said it, didn't it, up here? I don't know if it said the word. Maybe I'm missing it. But, okay, so let's do our test. Oh, I forgot to answer it. Here's our result. Okay, so what kind of test? These are independent samples. So we're gonna let's go to our chart. Let's go to our chart. So 2 independent means, I'm talking about 2 groups are not matched. They are independent. That's our situation. Nothing matched there. Use the 2-sample t-test. Okay. So we're going to do, so you got to put this group in L1, this group in L2 in your calculator. So you start by hitting stat and then edit. And then go to the top of L1 and hit clear and enter. So clear out the data from L1. And then put in L1 and L2 data. So get all that in there. This L1 data and this L2 data. Put those in. That's what this says. 2 independent lists of data are given. Put them in L1 and L2 by selecting data. And now select data. So now we're going to go to 2-sample t-test. So now let's do that. 2-sample t-test. 2-sample t-test. Select data rather than stats, because you're going to get your information from data, mainly this data and this data that we put into L1 and L2. That data will give us all of our decisions. So select data, and then what else does it say? After choosing data, and we always choose no for pooled. So we'll do that. We'll go back, choose data, to 2-sample T from data, and then it's going to say L1, or it's going to, let me write this out for you. it's going to say list 1. We're going to say L1. List 2 is in L2. Frequency 1 is always 1. Frequency 2, 1. Those are both 1. The frequencies are always 1. And of course, we're going to choose greater. And whenever it says pooled, we say no. And then calculate. So the test statistic, I get 1.42. P-value 0.086. All right, what does that mean? We were testing at what level? We were testing at the 0.01 level. So this is greater than 0.01, isn't it? The p-value, the probability of luck, is greater than we want. So in our case then, if the p is not low, right? Our p is not low enough. The p-value is too high. P is not low. The HO does not go away. So we keep the null. There's weak evidence. There's not strong enough evidence to reject the null. We fail to reject the null. We keep it. That's C. Fail to reject the null. There's not sufficient evidence to support the claim that the mean amount in city 1 is greater. So there's that. Oh, and that's actually the end of this problem. So there we go. So the main trick I want to emphasize, would you recognize that this matched pairs? No. Why are they not matched? Because they're kind of listed in side by side, so you might think they're matched. There's nothing connecting this number to that number. They're not married people. They're not actors and actresses from the same year. They're not connected in any way. They're independent. So we follow the instructions for independent means. So are you going to be able to recognize that on exam number 4? That's why I write these practice exams, to help you get ready and recognize things like that. This is not matched pairs. They're not matched. Now, let's look at a new example where they are matched, and I think we'll see the difference here. Look at that. So there's the actresses and the actors. Remember this problem? See how they're matched up? These two are from the same year. I don't know what year. Maybe that's 2018, who won the Best Actor and Actress Award. And there's 2017, and there's 2016. I don't know. But it says right here, the ages are matched according to the year. So they're matched. They're connected. They're dependent. So that's different than, as we look back here, City 1, City 2. They're just two independent lists. There's no matching. No match. There's no reason that this number connects to that number in any way. So they're not, there's no matching. All right. So getting back to it, this is matched pair data now. So let's look at our chart for that. We'll go back to our chart for matched pair. Now, I need to go find the new one. Okay, so these are matched pairs. Let's go look for matched pairs. What do? Put the data in L1 and L2, and then do L1 minus L2 stored in L3. So we're going to come in here and we're going to put this group in L1, this group of data in L2, and then, I should probably just erase this. So this group of data in L1, this group of data in L2, and then we need to take the differences between them, right? We need to subtract these and get the differences. This is how we handle matched pairs. I mean, the calculator is going to do it. We're not going to really do it. This would be like, this number minus that number. I don't know what that is, negative 41, and then this number minus that number, etc. You just got to get these differences, and that'll be L3. I'll go dot, 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 dot. You've got to find all those differences. Well, the calculator will do it for you automatically. So you put data into L1 and L2, and then you go second, quit. You quit the data entry screen. You get the data stored in L1 and L2 at this point. And then you go L1 minus L2 stored into L3. You basically took the L1 minus L2, the difference, right? See, that's the subtraction between L1 and L2, and you store it in L3 so that L3 will have all these differences will be in L3. How you get L1 on your screen is you hit second 1, L2 is second 2, and L3 is second 3, and the store button is lower left corner of your calculator. So what that does then is that takes all the L1 data, that whole list, this whole list of data, and the whole L2 data, this whole list of data, and subtracts them and stores the answers in L3. It basically computes all these differences, stores it in L3 for you. So you got the differences now in L3. So we'll never have to go back to L1 or L2. We'll just do all of our work on L3 where the differences are. Okay, so that's what the instructions say here. Put the data in L1 and L2 on this is the exam 4 notes, which will be real helpful for you. Exam 4 notes. Put them in L1 and L2, then go L1 minus L2 stored in L3. And then either do a t-test or t-interval. Choose data and that. Okay, so we're doing a t-test. Oh, I forgot to write out the claim. So what was the claim here? Somewhere there's a claim. Test the claim. So this is all in the way here. So this is L3 right here. The claim, actresses, the differences have a mean less than 0. So the mean difference is less than 0. That's the claim. The mean difference is less than 0. So this is always equals. The null is always equal. So this must be less than 0. That's the claim. This must be equal to 0 because the null is always equal. Right? We good there? The claim is that the difference is less than 0. Okay. So go to your calculator. Go t-test. On that, notice we're not doing 2 sample. Why not? Isn't this 2 samples? Yeah, but we've got all the differences now in L3. So we're just using that one list. That'll take care of it. Just go to regular t-test and choose data, not stats. Choose data, and it'll ask you for mu sub 0. Remember where that always comes from? That always comes from the null, which in this case is 0, right? The mu sub 0 is like h sub 0. It's to remind you of that. The list, now, what's this? Where's our data? L3. Everybody hearing me on that? L3, not L1, is where your data set is. That's where you get your data. So make sure you put L3 there. That's where the differences are, right? All these differences that the calculator figured out for us between, taking actress minus actor, subtracting the difference. It's all stored in L3. So your list of data is now L3. And the frequency, that's 1. It always is. And then we choose less than as our alternative hypothesis and calculate. And so when you do, I'm getting a t-value, negative 1.88, and a p-value, 0.046. Now, how does that p-value compare? What was our significance level? It's right here, 0.05. So that's less than 0.05, isn't it? So the p is low. The HO must go away, right? So bye-bye to the null. We're believing the alternative hypothesis because evidence is strong. There's only a 4.6% chance of luck. That's less than a 5% chance of luck. That's strong evidence that the difference is less than 0. What's our conclusion? Since the p-value is less than or equal to the significance level, I'm running out of room here, but you're supposed to reject the null hypothesis. reject the null hypothesis. There is sufficient evidence. Here, let's switch tables. So since p-value is less than or equal to the sigma level, reject the null hypothesis. There is sufficient evidence to support the claim that actresses are generally younger when they win the award, right? Because less than 0 means when you take the actress number, subtract the actor number, you get negative. You get a negative value, which means the first number was lower. When you subtract two things and get negative, it means the first number was lower, the actresses were younger. That's what we believe. There's strong evidence that the difference is less than 0. Less than 0 means negative, doesn't it? If I say a number is less than 0, that means it's negative. So the difference is less than 0. The difference is negative. That was the claim, and there's strong evidence in favor of it. So we believe that. All right, now they want us to do a confidence interval that could be used to basically do the same thing. Okay, so remember how we determine that. We go back here and we say suitable confidence interval. It depends on H1. What was our H1? Our H1 was less than. So if you have an H1 that is less than or greater than, you do 1 minus 2a. So our C level can be found. It's going to be 1 minus 2a. A, the significance level was what? On 0.05, yeah, right there. 0.05 significance level. And so A is 1 minus, or that's not A, I'm sorry. Let me get this together here. The A is 0.05. So the C level, the confidence level is 1 minus 2. Plug that in for A times 0.05. It's 1 minus 0.10. It's 0.90. So the confidence level is a 90% confidence level. So we come down here and we do a 90% confidence level. So we're doing, for matched pairs again, we're doing T interval. Choose data, mu0 and L3. So we're going to do a T interval on our calculator. And we choose from data. And the list, where's the data? L3 again, remember? L3, not L1. The differences are all stored in L3. Frequency, that's always 1. Each of those numbers in that list is just occurs once only. Frequency once. The C level, confidence level, we said is 0.90. Calculate, and you'll get numbers that go from negative 1.88 to 0.046. No, I'm sorry, that's not true. Let me try again. I'm looking at the wrong numbers. It is negative 17.4 to negative 0.2. All right, so what does that mean? Those numbers, if you go to the number line, here's 0 over here, negative 17.4 and negative 0.2. We're in this zone. That's where our confidence interval is. We are, 90%? We're 90% sure that the real difference between actress minus actor age is somewhere in the negative zone. Remember, if it was 0, they would be the same. If the difference between two things is 0, they're the same. 0 is not in our interval, so we're 90% sure, even more than 90%, that they are not the same. The difference is negative. The actresses are younger. What feature? Since the confidence interval contains only negative numbers, reject the null, right? The null said, go back to the null said, where was the null? The null said they were equal to 0. The difference was equal to 0. No, we rejected. 0's out here. We're 90% sure that the difference is not 0. We reject the null. Okay, so here we are in number 7. So it's talking about a popular theory is that presidential candidates have an advantage if they're taller than their main opponents. See if there's any data behind that. So here's the heights. President, main opponent. President that won, main opponent. President that won, main opponent. President, main opponent. President, main opponent, etc. So, now, the question is, which kind of data is this? Is this two separate independent lists? Or are they matched in some way? Clearly they're matched, right? This is a president and his main opponent. This is another president that won the election and his main opponent that lost to him. This is another president and his main opponent. They're matched. So these are matched pairs. They're dependent on one another, right? They're not independent. They're not separate. They're not completely separate. They're certainly connected. These two guys ran for president in the same year. These two guys, or maybe gal, ran for president in the same year. They're matched. Pair data. It's not independent. It's matched pair. Do you see how you recognize that on the exam? It's like the actors and the actresses. Okay, so which means we need to find the differences between them. We don't. The calculator will. Put data in L1, data in L2. So I'm just going to run through it quickly. We've done this a couple times now. So if you go back here to the right one. I can't seem to find it. Okay. Okay, so here we go. Two dependent matched pairs. There we go. Put data in L1, L2, L1 minus L2 stored in L3, t-test. Let's do it. Okay, so put data in L1 and L2, and then you go second, quit. You quit that screen, and you go L1 minus L2 stored in L3. So you store that in L3. Remember how you get this? You hit second 1, second 2, second 3. So now you've stored all the differences in L3. And then you go t-test on your calculator. Go down to t-test and you choose data. And then you choose, it'll say mu0, not always, I didn't write the null. What's their claim here? Differences have a mean greater than 0. So that's the difference greater than 0. The null is always equal. This is the claim. The difference is greater than 0. So this is 0 because it always comes from the null. H0 is like mu0. The list, where do we find all of our data? L3, not L1. Everybody seeing that? L3, that's where our data is. It's all stored now. The differences are all stored in L3. That'll be the subtractions, the differences. This number minus that number, this number minus that number, etc. The differences. So put that in and then say it's a greater than study, greater than, and calculate. So when you calculate, you'll get a t-value. I got a t-value of 1.85 and a p-value 0.062. All right, how does that work? 0.05 is their significance. That's greater than 0.05. So we say the p is not low enough. It's greater. The p is greater. It's not low. The HO does not go away. We keep the HO. Keep the null hypothesis. Evidence is weak. But it's not strong enough to reject the null. Since the p-value is greater than, trying to write this here, greater than the significance level, we fail. Let me write it right here. Since the p-value is greater than significance level, we fail to reject the null. There is not sufficient evidence to support the claim the taller president wins. Okay, last thing, confidence interval. How do we find the appropriate one? You can go back to the notes, suitable one, H1 greater than, less than, it's 1 minus 2a. Our H1 is a greater than, so sea level 1 minus 2a. The a, wasn't it 0.05? Yeah, right there, 0.05. 0.05, plug that in. Sea level's 1 minus 2 times 0.05. 1 minus 0.10, 90%. So come down here, do a t interval test on your calculator, and then say I'll take it from data, the list, L3 again, remember L3, not L1, and the frequency is 1, the sea level is 0.90, hit the buttons, confidence interval is negative 0.6 to 13.2. What does that mean? Well, here is 0, negative 0.6 to 13.2. See how 0's in there? And remember what 0 means. 0 is always where they're the same. If the difference is 0, they are the same. So they could be the same. 0 is in our interval. So these could be the same. These presidential ages could be the same. There's no difference. Since the confidence interval contains 0, fail to reject. The null, remember, says they're equal. They're equal to 0. The difference is 0. Well, 0 is in our interval. The difference could be 0. There could be no difference between the true average age of the president and their main opponent. Age could make no difference at all. It's possible 0's in our interval, so we fail to reject the null. We got to keep that null. The difference could be 0. 0's in our interval. There we go.